Welcome to Chemistry at Hononegah High School. I'm Brian Brown, and today we're going to look at our fourth set of notes dealing with gases and gas laws. Now, today we're going to look at the combined gas law as well as Dalton's and Graham's law. So we're going to look at three different laws. Now, the first one's going to be very similar to what we've been looking at in the previous situations. Combined gas law is at constant amount, which is the mass, which in this chapter we're going to always be dealing with moles. The product of the pressure and volume of a gas is directly proportional to the Kelvin temperature. So just like the other variable relationships we looked at, this is based upon what is a linear graph. And scientists found out that if you were at constant number of moles, when you graph the pressure volume versus the temperature, so the pressure times the volume versus the Kelvin temperature, you get a linear relationship. So that means PV over T equals K. And that would mean then P1 V1 over T1 equals P2 V2 over T2. And this is just like the previous three gas laws we looked at, Boyle's, Charles, and Gay-Lussac. And notice, it looks similar to them. Pressure and volume were always on top in all those laws. Temperature was always on bottom. And the temperature was always Kelvin temperature. So mathematically, you're going to solve this just like you did the others. So we're not even going to look at a problem with this because it's the same math we've been talking about. Now that brings us to the second law that I wanted to talk about today. Now we're jumping around a little bit in the chapter, but we had three laws that were easy to discuss today, and then you could practice in homework. So the next one I want to look at is another law that's fairly straightforward. Now, this is going to have a different feel to it than the other types of laws. It's not really looking at the relationship between two different variables. It's understanding the relationship between different gases at different pressures mixed together. And this is called Dalton's law, or Dalton's law of partial pressures. At constant volume and temperature, the total pressure exerted by a mixture of gases is equal to the sum of the individual or partial pressures. So what that really says is if we have a mix of gases, so let's say we have three gases, P1, P2, and P3. Could be oxygen, nitrogen, helium, whatever. If I measure the pressure of the individual gas in a container, and then I measure the pressure of the second gas and the third gas, when I combine them all together in the same volume at the same temperature, I'll notice that the total pressure is going to measure the individual pressures added up. And those individual pressures are often referred to as partial pressures because it's part of the overall or total pressure. And really, it's a fairly simple mathematical law then. One plus another has to equal what the total is. So if I know three of the four, so if they gave me the total pressure in P1 and P2, I could solve for P2. I'm sorry, P3 and so on. And remember, this keeps going. So if I have five gases mixed together, it would be P1 plus P2 plus P3 plus P4 plus P5 would equal P total. So what does that really look like as a problem? Well, let's say we have three different gases here, the green gas, the red gas, and the blue gas. Now I know the pressures of the green gas in this. They're all in the same room, so all at the same temperature, and they're clearly all in the same volume container. Well, I know the green gas exerts a partial pressure or a pressure of 200 kPa. The red gas was 500 kPa. And when I've combined them all together with the blue gas, notice it reads 1,100 kPa. So how do I know what the pressure of the blue gas was? Well, remember, the individual pressures add up to the total pressure. So 200 plus 500 plus x has to equal 1100. So solve for x. So 1100 minus the sum of 500 plus 200, which is 700. X has to equal 400 kPa. So that has to be our missing gas. So it's a nice simple add subtract law. So Dalton's law calculations are fairly simple calculations. Now, one of the things that you need to recognize with Dalton's law is this has implications whenever we collect gases. Because gases are typically these very fluid, hard to get in a container type substances that we often can't even see because they're colorless and odorless. So when we collect a gas, one of the most common ways to do it is to collect the gas over water. And whenever you see those three words, collected over water, which is how we always have to collect gases. We did this in a lab earlier, the one I called the rocket lab. When we collected the oxygen gas, we filled a pipette up with water, we put it on top of our gas collecting device, and literally we pushed the water out of the container and replaced it with oxygen gas. And at the level of the water, we could see exactly how much oxygen we had in there. So we collected that oxygen gas over water. Well, there's a problem. If I measure the pressure of that gas collected over water, it's not the pressure of the pure gas because water evaporates. And whenever I collect a gas over water, water vapor is going to be mixed in with it. So when I collect the pressure, it's not the pressure of the gas. What I'm actually measuring is the total pressure. And in order to calculate the pressure of the gas, I have to subtract out the pressure of the water vapor. So I have to do what's called a Dalton's law correction. So solving for the pressure of the gas, I get total pressure minus the pressure of water. Now the nice thing is, water evaporates to a constant equilibrium vapor pressure at a constant temperature, and it happens relatively quickly. So when I collect this gas over water and let it sit for a short period of time, I'm always going to have, at that given temperature, the same pressure of water vapor mixed in with it. And that's something I can look up in a table. Equilibrium vapor pressures at various temperatures have been measured for water. So I can actually calculate, or I should say, I can find the pressure of water by looking it up in a table. I found and measured the total pressure. I can subtract and find the pressure of my gas. But I have to remember to do this correction. So anytime you see those three words collected over water, the pressure that's in the problem is not the pressure of the gas. It's the pressure of gas versus water vapor. And you'll probably notice that they give two pressures in the problem, and one of them looks like it's unnecessary. Well, that's because you have to subtract those two pressures to get the pressure we really need to solve the problem. Now, the next thing I want to look at dealing with gas behavior is related to diffusion and effusion, two ideas that gases properties that gases have. And we talked about this last chapter, and they're going to lead to this thing called Graham's law, our third law to study for the day. Before we get to that, I want to remind you very quickly what diffusion is. Diffusion is the tendency of molecules to move from an area of high concentration to an area of low concentration until uniformly mixed. And this is because gases are in constant rapid straight line motion, so they're going to spread out. This is like perfume sprayed in the room. Initially, if I stand right by where the perfume sprayed, it has a very, very strong odor. But as the perfume spreads out within the room, that odor starts to decrease as it becomes less and less concentrated until eventually, in essence, the gas particles of the perfume fill the room. And at that diffuse level, I might not even be able to smell the perfume anymore. So if I had a box with two gases in it, separated by a barrier, and I remove the barrier, in a short period of time, the gases are undergo those constant rapid straight line motions and spread out and uniformly fill the box. Now, the second thing is effusion. Effusion is the rate at which a gas escapes through a small hole. And this is not a high pressure hole in a tire situation where the pressure outside literally pushes the gas out. This is a different situation. We just have a container with a gas in it, and it has a hole. Those gas particles are in constant random motion, and every once in a while, a gas particle is going to move and hit the wall, but there's no wall, so it's going to end up escaping. So that's what effusion is. Now, effusion and diffusion are related in that they're both depending upon the velocity of the particles. The faster the gas is moving, the faster it's going to diffuse and the faster it's going to effuse. And the relationship between those things is known as Graham's law. And what Graham's law says, the rate of diffusion of a gas is inversely proportional to the square root of the molar masses. Now, this law is kind of a mouthful. And mathematically, well, let's take a quick look at mathematically what it is. We have two gases at the same temperature. And what that means is they're at the same average kinetic energy. So the average kinetic energy of the one gas, gas A, is going to equal its mass times 1/2 times its velocity squared. And since they're at the same temperature, that's going to equal the average kinetic energy of the gas, which would be 1/2 times its mass times its velocity squared. Now, mathematically, these 1/2s are going to cancel, and I'm left with this relationship where the masses times their velocity squared equals the mass times the velocity squared of the second gas. Well, if I arrange the masses on the same side, and I get the velocities on the same side, I end up with the mass of A over the mass of B equals the inverse on the other side, the velocity of B squared over the velocity of A squared. And to get rid of that square root, I can square root both sides. And what I'd be left with is actually Graham's law. Now, mathematically, we're not going to do anything with Graham's law. So while this is true, this is not where we're going with this. What I want you to understand for Graham's law at this level of chemistry is the implications of this idea that the rates of effusion and diffusion are inversely proportional to the square root of the gas's molar masses. And remember, the molar masses were tied to velocities, and it was the inverse of the velocity. So what that fundamentally means is the bigger the mass, the smaller the velocity to get to the same average kinetic energy. So remember, we had this relationship a second ago. before I went through and showed you how you would determine what's actually called Graham's law. So remember, the 1/2s here are immaterial. They're going to cancel out. So when you look at this, if these two things are equal to each other, the bigger the mass is, the smaller the velocity has to be if they're going to be equal to each other. So if the mass of A is bigger than the mass of B, so I've got a big A and I've got a small b, this one is going to be moving slower to get to the same energy. And if they're at the same temperature, they're at the same average kinetic energy. So the implication that I want you to understand with Graham's law is that big molecules move slower and small molecules move faster at the same temperature. That's the implication about diffusion and infusion I want you to know. If I have perfume and the perfume is warmer, that means the velocity of the particles of perfume that get sprayed are going to be moving faster. And that means that they're going to spread out and diffuse more quickly. Another consequence of this isn't about perfume. It's about the gases in the room right now where you're standing or sitting and breathing. You have nitrogen and oxygen gas existing in that room. 80% of what you're breathing in is nitrogen gas, and about 20% is oxygen gas. Now, the molar mass of nitrogen N is 14.0, so N2 would be 28.0 grams per mole. O2, O is 16.0, so O2 is going to be 32.0 grams per mole. So when you think about it, they don't weigh the same, but they're in the same room at the same temperature. That means their velocities must be different. And remember, the lighter gas has to be moving faster to get to the same energy. The heavier particle will be moving slower to be at the same energy and the same temperature. So in this particular case, nitrogen particles that are colliding with you at a higher speed than the oxygen molecules, because as a lighter gas at the same temperature, nitrogen must be moving faster and oxygen must be moving slower. And those are the three gas laws that I want you to understand from today. And remember the last one? It's a conceptual understanding that I want you to have for the test. The other two, you definitely better know them mathematically.